Okay, today we will actually go over what we call the frequency response, and in particular, what the frequency response is actually your transfer function, h of s, when you evaluate it along the imaginary axis. So you can evaluate uh, your Laplace transfer function anywhere on the complex plane. Whenever we evaluate it on this axis, or the imaginary axis, we're going to call that the frequency response. So that's it. All of you are free to go. Lecture's over. The fish is sold. It's over. It's done. Okay, but why do we want to actually study the frequency response? Well, in particular, the reason we want to study the frequency response is because it actually tells us something about the steady state due to a cosine or sine input. So here I'm going to deviate a little bit and show to give you an idea of why this is significant. So let's just assume we have a circuit. This could be any circuit. We could be so you have a voltage source, a resistor, you could have a capacitor, you could have an inductor, you could have another resistor, you could have a capacitor, and so on and so on. And then this is your output, V out, let's say. And then you find the transfer function for this circuit, h of s. Now, let's just assume that this input here is a cosine omega t that has a Laplace transform. So that its Laplace transform is actually, it has an input in time, cosine omega t, so that its Laplace transform is simply 1/2 s minus j and 1/2 s plus j. So that's the Laplace transform of the input. And we know that the output is just the input times the transfer function. And so as a result, in order to figure out what the output is, we just need to inverse Laplace this expression. Now, let's say we go through a standard partial fraction decomposition. What we would end up with is a number of poles associated with the transfer function. And then we would have two coefficients associated with the two remaining poles for the input Laplace transform. Now, if we recollect, in order to find these coefficients, what we would do is take whatever's on the left, multiply it by s minus j omega to get this coefficient, the an plus 2, and then evaluate it at j omega. And so when we multiply this by s minus j, something's going to happen. So if I multiply this by s minus j omega, s minus j omega, what's going to happen is that the j omegas are going to cancel here, and here they're not going to cancel. And then when I evaluate at j omega, this will be 0, so this will be gone. And so the value of the an plus 2 coefficient is just half the frequency response. And I can do the same algebra, but this time with s plus j omega and then s plus j omega. And now I'm going to actually evaluate at s equals negative j omega. And what's going to happen is that the j omega factors will cancel here. And then when I evaluate at negative j omega, this will become 0. So this term will go away, and I'm going to be left with this factor here. And so in order to find the n minus 1 coefficient, I just have to evaluate the transfer function at negative j omega. So what that means is that my Laplace transform of the output will look something like this by plugging in the correct values for the cosine coefficients. And as a result, my time domain solution will have some part that's associated with the transfer function, and then another part that's associated with my input cosine, which will be the steady state solution. Now, that part that's associated with the cosine input has the magnitude of the transfer function evaluated on the imaginary axis at that omega value and the phase of that transfer function. And so as a result, if we evaluate our transfer function along the imaginary axis, that will actually give us the solution, the steady state solution, due to a cosine input. And so that's why it's significant when we look at this frequency response. In future classes, you're actually going to learn that we can write any input as a combination of sines and cosines in what we call the Fourier transform. And so as a result, if we know how a system responds to a single cosine, we know how to respond to any kind of input. But that's for future classes. And so as a result, we're very interested in this frequency response. Now, just to kind of solidify this more, when you were doing phasors, you were actually finding this steady state solution for a single frequency. In this class, we're actually looking at it for all frequencies. So like I said in the previous slide, when you solve for phasors, you typically were assuming that the input was some kind of cosine and omega, and then you solved for the output that was that. That's almost like evaluating your frequency response at a single frequency. Okay, so that's basically what the frequency response is and why it's important. Now we're going to actually talk about plotting the frequency response. And to do this, we typically have to introduce some conventions that are typically used to report these things. But before we do that, let's just plot it. So if we look at this circuit here, the H of S, if this is the output, then it's just going to be IL sub S divided by CL plus ZC. Sorry, IL sub S. Sorry, I apologize. So you have V in sub S divided by ZL plus ZZ equals IL sub S. So the output current is equal to, and so you can just rewrite this as, well, if we assume that the input is 1 so that we can find the transfer function, so H of S, 1, and then we're going to get that this is just equal to 1 over SL plus 1 over SC, and then we can multiply by S and divide by L. So we're going to get S over L divided by S squared plus 1 over LC. So now that we know H of S, we can find the frequency response by plugging in j omega for S. So we're going to get, we're going to get j omega over L divided by j omega squared plus 1 over LC. So all I did was plug in j omega for S in this expression. And then once I have that, I can just simply realize that this is a negative omega squared, and then that gives me this expression here. Okay, So that's our frequency response. Now we can evaluate this for different values of omega and extract the magnitude. So if I evaluate this at 1, I'm going to get kind of J1 over L divided by 1 squared plus 1 over LC negative. And then if I take the magnitude, that's just going to be equal to 1 over L 1 plus 1 over LC. And then I can just plot it. And then as I keep plotting it, I'm going to get different values. So here I plugged in for L 1 microhenry and 1 millifarad. And this is what that magnitude plot looks like. And then this value here would be kind of 1 over LC. When the frequency equals 1 over LC, the current will go to infinity because this will behave like a short circuit. And additionally, we could look at the phase of this. So if omega is really small, then this will be 90 degrees because it's going to be purely imaginary. And then if omega is really big, then it's going to be negative 90 degrees because it's going to be negative and purely imaginary. Yeah, so that's basically why you see this transition in the h of j omega from pi over 2 to negative pi over 2. So this is like 1.5 whatever, which is pi over 2. Yeah. Okay. So what we're going to do now is actually develop a way of plotting these things in a very, for both the magnitude and the angle of the frequency response in a systematic way. And to figure out how to plot these things, first we need to introduce the decibel scale, which is what people typically use to make plots of the frequency response, and then an approximation that we do to generate these plots. Okay, so just as a reminder, we're going to be looking at our frequency response, sorry, at our transfer function along the imaginary axis. And in particular, we know that our transfer functions will always be the ratio of two polynomials, which can be written in this format here, where you have the highest order coefficient have a coefficient 1, so you factor out that value. And yeah, so basically both of the polynomials can be written as a product of monomials. And as a result, when I look at the magnitude, I just take the magnitude of the individual monomial terms. And when I look at the angle, I just have to look at the angles of the individual monomial terms and subtract the individual monomial terms. Now, the reason why these expressions are important is because we just need to learn how to plot a factor that looks like j omega minus ck, or 1 over j omega minus pl, and then we'll learn how to plot basically a general transfer function. Okay, so here I'm just basically kind of stating something that you should know now, which is that our transfer functions are always ratios of polynomials. We can find all the roots of those polynomials and write it in this nice compact form. And then if we plug in an imaginary quantity for s, we can take the magnitude of the individual parts, and then that's going to give us a plot of the magnitude. And then same thing for the angles. All right. Okay. So here's another example of a frequency response. I'm just going to skip this for now so that we can move on. And then here's some code on how to plot it. And I also introduced kind of another important concept, which is the decibel scale. Uh, Engineers typically report this magnitude not in a linear scale, but in what we call a decibel or a logarithmic scale. So if you ever buy headphones, you notice that a lot of times you get this frequency response. And so here's kind of like a 20 hertz or the trebles, and then kind of, 20 hertz are the bass, and then the trebles are kind of the higher frequencies, 20 kilohertz. And typically, like they'll show you kind of what the headphones frequency response is. And then the y-axis of this plot is typically dB or decibels. That corresponds to actually a logarithmic scale where you take the magnitude of the frequency response, you take the log base 10 of it, and then you multiply by 20. The reason we present things in decibels is because if you looked at our previous plots, they went to 0 pretty quickly. And so you don't get a lot of information because if your thing goes from 10 to 0.1, if you look at it on a plot where you have kind of 1, 2, 3, 4, 5, 6, 7, so this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, then 0.1 is going to be here. So your plot's going to look like this. And you won't be able to distinguish from when you go from 10 to 0.1 to 0.01, because it's just kind of 1.1 will all be kind of squished down here. So you won't have any information for those lower values. And when it comes to sound in particular, our ears are like a logarithmic scale. So if you perceive something as twice as loud, it's actually 10 times louder. And if you perceive it as 4 times louder, it's usually 100 times louder. And so as a result, your ear is able to actually distinguish between 0.1 times the signal and 0.01 times the signal. But the plot doesn't actually kind of, this plot here kind of tells you that 0.1 or twice as, or half as loud is the same as 4 times less loud. And you know that that's not the case. And so as a result, that's why we do things in logarithmic scale, because in the case of a logarithm, in the case of a logarithmic scale, well, the log base 10 of this is 2. The log base 10 of this is actually -1. And the log base 10 of this is actually -2. And so in decibels, this would be 40 decibels. So this would be like right here. So that would be 10. And then -1 would actually be -20. So it'd actually be down here. And then -40 would be actually down here if we were to keep going this plot right here. And so as you can see in this kind of plot, you would be able to very well distinguish between having a magnitude of 10, having a magnitude of 0.1, and having a magnitude of 0.01. So that's why we use a decibel scale. All right. Okay, so we're going to basically take our expression for the frequency response and we're going to basically plug it in here in order to get our expression in decibels. On this slide, you can see here on the left, there's actually a MATLAB code to generate these figures. So if you ever want to generate these kinds of figures, that's kind of what you would write. This semi-log x is actually what generates these kinds of plots. And then subplot allows you to have, in this case, 2 figures stacked. If you made this 2 by 2, then you could have actually another 2 figures here, and so on. And so this is the first figure, and then the second figure will be the angle, which I'm also plotting on a log scale. Yeah, so this is just a way that you could plot your frequency response, and this is just a very simple code to do that. not going to go over it because our class is not on MATLAB. This is just for those of you that kind of want to know how to plot these things. Well, how to plot them in a computer, because actually this whole class is about how to plot these things. But okay. Yeah, okay, so I'm gonna basically convert my magnitude of the frequency response into a dB scale. So I just plug in my expression for the magnitude into this log, but do realize that there's this property of logs that it takes products and it converts them to sums, and it takes division and it converts it to subtraction. And so when I take the log of this big complicated expression, I actually get the sum of the logs of the little expressions. Okay, so that's basically what our what our frequency response is in the logarithmic scale. Now, if I have the value in dB and I want to go to linear scale, all I have to do is take 10 to the h of j omega in decibels, and then divide that value by 20, and that's going to give me h of j omega in either volts per volt, volts per current, or a linear scale. But we're going to be using the decibel scale mostly, but do realize that when you use this formula, in order to figure out what the steady state is, you need to convert it back to the linear scale, and we'll go over some examples later. Okay, so our goal, like I said earlier in this class, our goal is to learn how to plot these frequency response plots. And that's really the aptitude that you need to get out of this. So, I told you, well, there's two aptitudes. You need to know how to use these plots to determine the steady state, which is very simple. You just evaluate them at the value of omega, who's of the input. And then you need to know how to plot them in the logarithmic scale. You don't need to know why we do this. I mean, it probably will help you understand why we do it, because if you're just learning stuff just to learn it, it doesn't really stick a lot of times. But if you understand why it's important that you learn it, it helps you memorize or motivate you to learn it. So that's why I go over all this extra stuff. But what you actually need to know is what I'm about to go over now, which is how to approximate it. So what we're actually going to do when we plot these things, we're going to make a very crude approximation. We're going to approximate this as approximately equal to 20 log base 10 of capital X when capital X is less than omega, greater than omega. And then we're gonna approximate an expression that looks like this by 20 log base 10 of omega whenever omega is greater than capital X. So basically, we're just going to pick the bigger one of the two, and we're going to say that that's the value of the magnitude. Now, why do we want to do this? Okay, let's look at an example. So let's say this factor here was j omega plus 10. Okay, so from here to here, let me use a different color. So from here, so anything kind of, let's say this is a frequency, here, let me just erase really quick. So let's just say this is frequency 0.1, this is frequency 1, and then this is frequency 10, this is frequency 100, and so this is the omega axis, and this will be the h of j omega axis. So if we look here, this is the value of our x. Oh, okay. So in this half, we're going to approximate this using this expression. So basically, this is going to be 20 log base 10 of 10, which is equal to actually 20 times 1, because the log base 10 of 10 is just 1. And so that's just going to give us 20. So we're just going to approximate this here up to here by 20. And then in this region, we have that omega is going to be bigger than 10, or x. So remember, we're assuming that we're doing this expression, 20 log of j omega plus x. So now we're going to assume that this is 20 log of j omega base 10, which of course will just be equal to, well, in this case, so remember that the log base 10 of, so if omega is 100, it's just equal to 2. So this is the log 10 of omega. If omega is 1,000, this would be equal to 3. 10 to the 4, it would be equal to 5, and so on. So at 100, this will be actually 40. And then at 1,000, this would be 60. And so our plot, approximation of that plot will look something like this. 40 and 60. So as you can see, generating plots using this approximation is actually quite straightforward. And I'm going to go over more examples. Here I just wanted to introduce the approximation and just give you an idea that all we're doing is when omega is less than x, we're just going to use this expression to approximate each of these monomials. When omega is greater than x, then we're going to use this expression to approximate these monomials. And then in the next slide, we're going to actually go over an example, and you will get an idea of how to generate these magnitude plots in decibels. Okay, so here's the approximation written more cleanly. There should be a magnitude here and a magnitude here. Yeah, just because it's, well, we're always going to assume that those x's are positive, but whatever. Yeah, so let's go ahead and look at a more complicated example. So let's say we want to approximate plots of the frequency response, the magnitude of the frequency response of this transfer function. So we first have to evaluate it at h of j omega, and then we need to basically, once we evaluate it at h of j omega, we need to basically plot it. So we're going to divide our expression into multiple expressions, and we're going to make our approximation. So first, we're going to look at what happens when omega is less than 1. Well, if omega is less than 1, remember, we're going to pick the bigger one of the two arguments. So we're just going to approximate this as 20 log base 10, 1. And then here we pick in the biggest one of the two, which is the 10, because remember, this is less than 1. So we get 20 log base 10. And then again, we're going to pick the 100 because 100 is greater than 1. So minus 20 log base 100. So this is the approximation we're going to use whenever omega is less than 1. Now, when omega is between 1 and 10, well, for this expression, the omega factor is the bigger one. So now we have to pick the omega. In this case, the 10 factor is still bigger, so we keep the 10 factor. And the 100 factor is still bigger, so we keep the 100 factor. Now, in the next range, we have that from 10 to 100, well, this omega is still bigger, this will be bigger because this is bigger than 10. Now it goes from 10 to 100. And the 100 is still the bigger one. So now you have omega. So you have plus 20 omega minus 40 omega, which gives you positive 20 omega. And then you are, wait, sorry. Oh, God. Yeah, sorry. Which gives you negative 20 omega. So 20 minus 40 gives you negative 20. And then you're left with the 100 factor here. And then finally, at the very last one, whenever omega is greater than 100, you're going to approximate all three of them as log base 10 of omega, because now omega is bigger than all of the things you're adding or subtracting or whatever. So as a result, this becomes 20 minus 40 minus 20 becomes negative 40. So all we're doing is we're applying this approximation, and now we are approximating this expression here for our frequency response as this. Okay, now we're ready to plot it. So let's look at our plot of our frequency response. And just to kind of make this easier, I'm gonna write down what if I have omega here and then the log base 10 of omega. So if omega is 1, then 0, 2, sorry, 10, then it becomes a 1, 100, 2, 10 to the 3, 3, 10 to the n, n. Okay, so now let's make this plot. So we're going to start here at point 1, then we're going to go to 1, then to 10, then to 100, and then to 1,000. I think that's enough. So our plot will start by, for values less than 1, this is a constant, so there's no dependence of an omega. So we're just going to, so it's just going to be 20 times 0 minus 40 times 1, because the log base 10 of 10 is just 1, minus 20 times 2, because the log base 10 of 100 is 2. So we have negative 40 minus 40, which gives us negative 80. So we're going to start at negative 80 decibels. Okay, so this thing will be flat up to 1. Then after that, we're going to have, well, this is still negative 40 times 1, and this is still negative 20 times 100, sorry, times 2. So it's still, so this will be actually, this is actually equal to 20 log base 10 of omega minus 80. Okay, so when it's 10, the log base 10 of 10 will actually be equal to 1. So you have 20 minus 80, so this is going to become so this is going to become wait, log base 20, oh shoot, I did this wrong. Okay, I apologize. So I should go up, right? So this should be negative 60, negative 40, negative 20, and then here you have negative 100, negative 120, negative 140. So at 10, we're going to have negative 60, so it's going to go up by 20. Now at 100, we can keep using this expression up to 10, and then from 10 to 100, we have to use this new expression here, which is basically negative 20 log base 10 of omega minus 20 times 2, which is 40. Okay, so let's say omega is 100. So we're going to plug in 100 here, which is going to give us 2. Right? So we're going to get 0. So we're going to be like up here. No, wait a second. 20. Negative 20 times 2, which is going to give us, yeah, 0. So we're going to be up here basically 0. So we're just going to go up here down to 0. Minus, oh, whoa, sorry, I apologize. It's minus and minus, so it's actually negative 20 times 2, which gives us negative 40, minus 40, that's going to give us negative 80, so we're going to go down here, back to negative 80. And now we're got to do this last expression, which you have negative 40 omega. So basically, this becomes, if we evaluate it at 10 to the 3, negative 40 times 3, that's 120. So we're going to go down to 120, and then it just keeps going down. So that's going to be our frequency response plot for the magnitude. So that's it. That's basically how you plot these Bode plots. Now, there's actually a shortcut kind of way, and I'm going to tell you what it is. If you looked at our approximation, okay, whenever the zero or pole was bigger than the value of omega, you have the log of a constant, or the log of that zero or pole. So that means there's no slope. Now, the moment your omega value becomes bigger than each zero or pole, you get a slope of either positive 20 if the omega is becoming bigger than a 0, because here there's 20 log base omega per factor of 10. And whenever you pass a pole, you get a negative 20 slope per factor of 10. And so a heuristic you can do to draw the Bode plot is the following. You start by basically taking your h of s, okay? And then you look at the locations of the magnitudes of the zeros on the omega axis, and you denote them by a vertical line. Cool? The poles, and then you denote also the location of the poles by vertical lines. And then you start by figuring out what the slope will be in each subregion. So if I look to the left of here, there's no zeros or poles that are less than my given value, so my slope will be 0. In this region, I have a pole to the left, so my slope will be negative 20 per factor of 10. If I look here, I have a 0 and a pole, so my slope will be 0. And then if I look here, I have 2 poles to the left, and I have 1 0, so my slope will be positive 20. Sorry, negative 20, because you have a negative 20 per pole and a positive 20 per 0. Once I know my slopes, I can just basically figure out what the value is at this point and then just draw my plot. That's one way to generate these plots. So we're going to go over an example of using this heuristic, which is actually equivalent to what we just did. We're just basically taking a shortcut way by saying, when we're on this region, there is no zeros or poles, so I'm just gonna approximate this as a constant. As soon as the omega, the omega becomes bigger than any pole, then we have to modify our expression and so on. And each time we cross a pole, we have to change our approximation. Okay, so let's just yeah, so let's make sure that I went over everything. Yeah, okay, so one last thing is that whenever your response falls by 3 decibels from the maximum, that's called a cutoff frequency. And the reason this is significant is because when you fall 3 decibels, it means that your response has fallen by 1 over the square root of 2. Okay, let's keep going. All right, so let's look at another example using our approximation. Okay, I can write again. Okay, so I'm just going to use the heuristic that I came up with, which was basically I said, so remember, in this region, so I'm going to look at where all the zeros and poles are. So I have at 1, I have 2 poles, and then at 100, I have a pole, 1 pole, and then I have a 1, 0. Okay, now if we look at this expression, if we use our approximation in this subregion, we're going to approximate our frequency response as log of 10 minus the absolute value, well, all of this times 20. So, oh God, okay, let me just, this is not a good idea, but I'm going to do it anyways. 20, and then I'm going to have log, and log base 10 of what? 10 minus log base 10 of 1, 2 of these factors, because there's a squared, minus log base 10 of 100. Okay, so in this whole region, since there are no poles to the left of the region or zeros, we have that our slope equals 0, and the value will actually be determined by this expression here. So we have log base 10 of 10, that's just 1, 2 times log base 10 of 1. Well, the log base 10 of 1 is just 0, so that's 0. And the log base 10 of 100 is just 2. So we have 1 minus 2, which gives us negative 1, times 20 gives us negative 20. So we're going to have that this is constant here. Okay, at this point, we're going to cross 2 poles. So according to my heuristics, we should update our slope to be negative 40 decibels per decade, because we cross 2 poles. But if we look at how our expression is modified, now we have 20 log base 10 of 10 minus 2 log base 10 of omega minus log base 10 of 100. So you see here, 2 times 20 becomes negative 40, and that's where we pick up that slope of negative 40. So we know that this is going to fall by 40 per factor of 10. And then here we're going to pick up a 0, so our slope gets modified to negative 20. So it should go here. Now I'm gonna actually draw the expression just to kind of solidify this, that here what the approximation we would have to do would be 20 log base 10 of, now in this region, the omega factor is bigger for the first term because it's bigger than 10, minus 2 times log base omega minus log base 10 of 100. So as you can see, there is 2 poles and 1 0. So 1 minus 2 gives you -1, and then times 20, that gives you a slope of 20. Finally, here we cross another pole and we should get a slope of 40. So if we look to the left of here, there is 3 poles and 1 0. So the slope is -40. And so now we have 20, 40. So we're here and then here. And that's our magnitude plot that we have. So here the slope is 0, here the slope is -40, here the slope is -20 per decade, and here the slope is -40 per decade. And that's it. That's how we plot our magnitude plot. Now, there's one case that we haven't considered, which is what if you have a 0 at 0, which is kind of what we're going to plot next. Yeah, so here's the plots that this is the actual correct plot. And if you looked at our approximation, before we move on, if you looked at our approximation, it basically went from here, then it went down 40, so it went down to here, and then it went down 20, then it went down to here, and then here it actually started, it ended here, so then it went down like that. So our approximation actually fit pretty well the light blue line, as you can see. Here there's a deviation, which is kind of because we're actually, at this point is when like absolute value of x is approximately equal to absolute value of omega. And so our approximation is not as valid. What we should do at this place is actually replace this by log 2 times the absolute value of x, or something like that, or actually the square root of 2, I apologize. And so per pole that's located here, this error here will actually be 3 decibels times 3 dB times number of poles, approximately. But let's not worry about these imperfections. What we want to do is get the global picture so that we have a way to kind of graphically think of these things from a high level. All right, let's go. So now let's try this one. So look, we have a 0 at 10 to the negative infinity. So there's kind of a 10 to the negative infinity. There's a 0. And then there's 2 poles at 1. 2 poles. And then there is a pole at 100. Okay, so here what we're going to have is actually that our approximation would be log of omega, right? Because there's this 0. This is like s plus 0. So everything is going to, any frequency is going to be bigger than 0, basically. Minus log of 1 minus log of 100, and this should be 2, and then all of this needs to be multiplied by 20. Okay, so if we want to evaluate the value here, what we're going to get is actually, well, this is 0.1, so this would be -1 minus 2 times 0 minus 2. So that's going to give us -3 times 20, so that's -60. So it should start here. And then the slope here, if we look to the left, there's a 0 way out there at 0 frequency, so there should be the slope will be 20 here. Then there's 2 poles here, so the slope would become -20, and then there's a pole here, so the slope will become -40. So if we want to plot this, we're going to go up by 20 from here to here, then from here to every factor of 10, so from 1 to 10 we go down 20, and then from 10 to 100 we go down another 20. And let me just, I kind of drew this lopsided. It should be kind of flat. I can't draw, but basically this should be 60, and if I could just clean this up really quick. So this should be 60, and then here we have a slope of 40. So here we're at 80, we should be at 120, and then 160. So this one will look like this. So because we have a 0 at 0, our graph actually starts with a positive 20 slope. Okay, so that's how we plot our magnitude Bode plots. And so here's the actual plot of the Bode plot. So remember, to the left of here, there's 1, 0. To the left of here, there's 1, 0 and 2 poles, so it becomes -20. And then to the left of here, there is 1, 0 and 3 poles, so that gives you -40 slope. This is the approximation that we drew on the previous slide. This is the correct answer. And you can see that for such a rough, quick, it gives you a pretty good estimate of what the plot will actually look like. So one thing that you might be actually wondering about is why do we even bother plotting these things if the computer can give us this blue line? I'll tell you why. Because when you see this, a lot of times you're going to be presented with this, and you need to build a mental picture of how this is going to look without even drawing it. And this gives us a quick, rough perspective of what's going to happen. As soon as you look at this picture, you should know, oh, if the frequency is greater than 100, the frequency response will go down by a factor of 40 decibels per factor of 10. And so if someone's like, I'm trying to design this circuit to work up to 20 kilohertz, and then they show you this, you're like, hey, my friend, you know, this 100 should be closer to 20,000 because the response of this thing will be terrible at 20 kilohertz. But so we need to develop this kind of very quick way of viewing these responses so that we know how to modify the circuits without doing complicated math. That's the only reason why we're going over all of this. I hope this kind of gives you an intuition of how to interpret. On another way, when you look at this plot, you should kind of already know, hey, these poles here, if you need the response to be here, these poles need to move out. So you need to modify your circuit to get those poles to the right. So this is why we actually learn these simple plotting things. It's not because you're going to generate these plots in a PowerPoint and people are going to be like, wow. No, it's because they allow you to give you that simplistic way of looking at circuits that allows you to do engineering. All right, let's go. Okay, so let's say I gave you this Bode plot, and I told you this was a simple low-pass filter. What's the order of the pole that you cross around here? Can anyone tell me? Well, what is the slope from here to here? So what you can do is just look at the slope. And what you see is that actually we fall by a factor of -60 decibels. 60 or 80? This is 10 to the 3, this is 10 to the 4. Okay, so I should go down to here. Yeah, so it's more like 60, not 80. Yeah, so you fold by 60, so that tells you that what is the order of the pole? Well, the order of the pole has to be 3 because your slope is negative 60. It goes from 1 to negative 60. Now, what is the cutoff frequency? Well, to find the cutoff frequency, you just simply, this is the maximum, and you just look at the frequency where it goes down by 3. So here I actually zoomed into this region, so that's what you're actually looking here. 1 decibel, 2 decibel, 3 decibel. So cutoff frequency is actually 50. So those are two things that you need to learn how to extract from circuits, from these plots. Okay, so the cutoff frequency is approximately 50. Okay, so that's magnitude Bode plots. Now we're going to actually go over, we're going to spend the last 20 minutes of class going over how to plot the angle. And for the indie students, I'm not actually going to have that on the test, but I do want you to see what we do to actually plot these degree plots. What will be on the test is something that looks like this, which is basically asking you to interpret these plots. So if you recollect, if I ever ask you for the steady state, you should be able to get it from looking at the frequency response. So if I give you that Vns of t is, if I give you that Vn, remember this formula that we saw at the beginning of class, that if Vns of t equals cosine omega t, then the steady state or the phasor response V out of t will actually be equal to h of j omega in a linear scale cosine omega t plus the angle of h of j omega t of j omega. Sorry, it should be a plus. Okay, so if I told you that the input is 3 cosine 1,000, that means that your omega is 1,000. So you can look at your frequency response at 1,000. And then you can look at your angle at 1,000. So this is negative 90 degrees. Now, this is in decibels, so you need to convert to a linear scale. So negative 60 dB. So remember that if you go from dB to linear, so let's say you're at 40, that means 100, 20, that means 10, 0 means 1, negative 20 means 0.1, negative 40 means 0.01, negative 60 means 0.001. So in a linear scale, this is actually 0.001. So we're going to have basically 3 times 0.001, which is what I read here, cosine 1000 t plus 25 degrees plus what I read from here, which was negative 90 degrees. That is V out. Now, of course, you can combine this 90 and 25, and that's going to give you 65, negative 65. And then you can multiply this out. So I'm just going to write out the correct solution. So it's going to be 0.003 cosine 1000 t minus 65 degrees. That's going to be your output. So that's why this is significant. See how fast we could get the output by just looking at the magnitude and angle Bode plots. Okay, so here's kind of what I just said in the... Okay, so we're going to now look at what happens when our frequency response now we're going to look how to plot the angle. In particular, we're going to basically, just like before, just look at our simplified expression, and we're going to derive a set of approximations for it. So specifically, we're going to say that whenever omega is much smaller than x, we're going to approximate this as approximately equal to the angle of x, or negative the angle of x. And then when omega is equal to x, we're actually not going to approximate it. We're just going to evaluate the angle by evaluating the angle of the expression. And so finally, so basically if omega, so we can just replace this with magnitude of x. And then finally, we will, whenever x is much smaller than omega, then we will replace this by the angle of j omega, which will be equal to pi over 2. Okay, so that's basically how we're going to approximate this. And so now let's look at the next slide where we're actually going to use this approximation to construct our functions. Yeah, so I forgot, anywhere in between, you're just going to linearly connect the results. So here's the approximation we're going to write on that I wrote on the previous slide. So basically for omega, let's say that this was the angle of x, negative the angle of x. And so we're going to have up to x over 10 frequency. We're going to have basically constant. When it's x, this is actually negative. Well, it's actually going to be, if we look at our graph, we have whatever x is minus 90. So basically let's just assume x is real, so that this is actually x is actually the 0. So let's just replace this with a 0. And then we have to minus 90, which would actually put us at 45 degrees, negative 45 degrees. And so, or actually, sorry, I apologize. That would put us here, which would be positive negative x, which is here. And then you have j, which is here. So that would put us at pi, at whatever the angle is of negative 8. So this would be kind of negative 180 or pi. And then that's going to give us pi minus pi over 4. So at x, we're going to be somewhere here. Minus pi over 4. Finally, if x becomes very large, well, the angle of x right now is 0, so we have pi over 2 minus the angle of x. So we're going to get 0 here. Cool. So that's basically our approximation, and then we connect it, and then that would be the approximation we make. Next slide. Stop. Okay, so let's use our approximation to plot this. So we have the angle of j omega plus 10 minus the angle of j omega plus 100. That's equal to the angle of h of j omega. So we're gonna, whenever omega is less than 1 or equal, we're gonna have the angle of 10 minus the angle of 100, which is just 0 because the angle of a real number is 0. So we're just gonna have 0 up till we get to 1. And then when omega equals 10, we have to actually use our formula to evaluate this one. So we have j10 plus 10 minus the angle of j omega plus 100. So here this is pi over 4 minus wait. So this one we can still approximate as the angle of 100 because it's much smaller, minus 0, so we're going to get pi over 4. So when omega equals 10, we're going to be somewhere around here, which is pi over 4, which is like 1.7 something. Now, when omega equals 100, we're going to have that this one is j omega, so we just replace by pi over 2 minus the angle of j 100 plus 100, which is, again, pi over 4. So we're going to actually end up with, at 1,000, we're going to end up as pi over 4. So this thing will actually go up, up, and then it's going to go down to that. And then finally, when omega equals 1,000, we're going to have the angle of j omega minus the angle of j omega, which is just 0. So this is our approximation. So here you notice how I added this little peak? Well, here it was going up, and then here it's going down. So I just kind of, at the center, just approximated as that. So you kind of have to extrapolate that middle region where one gets approximated as a constant and then the other one gets approximated as linear, and just kind of make it into a smooth curve. Okay, so let's see how close our approximation is. So we can see it approximately matches because what we got was that up to 1, it was constant, and then we said it was going to go to pi over 4, and then here it's going to be constant, and then what we drew was something that looked like this, basically. So we at least got an idea of what the angle plot would look like, which is kind of what we're trying to do here, develop some kind of intuitive, quick approximation of what the angle function should look like. Let's do one more example and then call it a day. Okay, so here our smallest pole is 1, so we're going to have to look at up to 0.1. We're going to have to kind of look at numbers where omega is smaller than 0.1 to begin with. Okay, so I guess we're drawing with that color. Omega equals, or it's less than 0.1, we're going to have the angle of 10 minus the angle of 1 minus the angle of 1 minus the angle of 100. So that's just 0 up to 0.1. So here, oh wait, that's negative. So here, once we get to 1, at omega equals 1, we have kind of the angle of 10 minus the angle of 1, or j minus 1, minus the angle of j minus 1, minus the angle of 100. So at 1, we're going to have 0, pi, this is pi over 4. This should be plus 1. I don't know why I keep writing. So it's negative pi over 4, negative pi over 4. And then this is 0. So we have pi over 2. So at 1, we should be like around here. And then at 10, we're going to have the angle of j10 plus 10 minus the angle of j omega minus the angle of j omega minus the angle of 100. So this is pi over 4 minus pi. So we're going to be 3/4 pi. So we're going to be at 0.75 less than pi. So pi is here, right? 3.14, and subtract 0.75. So somewhere around here, let's just say, or 1.5 plus 0.75, yeah, somewhere around there. So we're going to have something that looks like this, and then like this. Probably this will go down and then up, but here, let's just do it like that. Okay, and then at 100, so wait, this is 10, this shouldn't be 100, so this should be up here. So we said that, yeah, somewhere around here. So like this. Now at 100, this becomes j omega. So now at 100 we have, so at omega equals 100, we have to approximate this as j omega minus j omega minus j omega minus j 100 j100 plus 100. So we're going to have this 2 cancel, negative pi over 2 minus pi over 4. So at 1,000 we're going to be basically constant. And then finally, whenever it's bigger, where we're going to have j omega minus j omega minus j omega minus j omega. So these two will cancel, and you're going to be left with 2 of them. So we're going to be at pi, somewhere around here. That's at 1,000. So it's going to look something like this. Let's look at the correct plot and see how well we got it. And so one thing to note here is that the slope, we know it's going to be wrong because it has to like smoothly flip. So there's probably going to be like a little kink there. So here's the correct answer. And if you recollect, what we drew was something that looked like this. Then at 1, it was already at pi over 2. So it was around here. So it went something like up to here. Then it went down like that. And then at 1,000, it was down to here. So then it went down like that. And then we said it went flat. And then we said it went down. And then we said it became flat again. And then after I finished drawing it, I kind of said, well, look, here it's going down. Here it becomes constant. Here's going down. So it's likely that it's going to bump up because the slope has to continuously change from negative to constant. So it has to kind of go up to go back down. So that's why I drew that little gap. But that's basically it. Okay, so that's all I have for today. So I just went over this angle stuff. Like I said, indie students, this is not going to be in the exam. This is just kind of for completeness' sake. I would prefer that you really, really well understand well how to plot these magnitude plots. The angle thing is just for completeness. So now you know, and if you want to come back and kind of study this more, as you could tell, like it's actually a lot harder to plot these angle things because the approximation is not as clean. Because you can't just kind of pick the bigger one of the two. In between, that's not gonna fly. But it's just good to kind of, for completeness, to go over everything, and so that's why we go over it. So that's it, and I will see you next time. Okay, bye.